Welcome to our lecture series on engineering mechanics statics. So for this lecture video, we will discuss about the following topics. So the first one will be the definition of equilibrium. The next one is free body diagrams. This is for coplanar equilibrium analysis. Then we have the coplanar equilibrium equations and equilibrium analysis for single bodies. So let's start first with the definition of equilibrium. So we will start our discussion with the definition of equilibrium. A body is in a state of equilibrium if the resultant of the force system that acts on the body disappears. Or basically, what is meant here is that the resultant force is equals to 0 and the coupled resultant is also 0. Technically, equilibrium means that both the resultant force and the resultant couple are equal to 0. So basically, there will be no translation and rotation in the body. So from our previous discussion about resultant, the resultant force and resultant couple tends to translate and rotate the body respectively. In the absence of the resultant force and couple, where the body is in a state of equilibrium, the body will now be at rest because there will be no resultant force and resultant couple. So that is why the subject statics is about this topic, which is equilibrium analysis. So from the concept of resultants of coplanar force system, so the resultant R, which is passing through an arbitrary point, which is point O, with its components Rx and Ry, can be calculated using the following equation. So we have this from two-dimensional or coplanar force systems. Then the resultant couple can be calculated using this formula. So it will depend on what type of force system. It may be coplanar, general, or coplanar concurrent, and parallel. So from the definition of equilibrium, what will happen to the resultant Rx, Ry, and coupled resultant Cr will become 0 because that is the definition of equilibrium. We can now derive the equations of equilibrium for coplanar force system. So this is the general formula for equilibrium analysis you see in the coplanar force system. So the summation in the equations must include all forces. So this is the new one that I will discuss about equilibrium. When we say about forces in equilibrium analysis, there are two types of forces. We have the applied forces and the reactive forces or the reactions. So these reactions are the forces that provide support on the body. So it tends to hold the body in place. That is what we call the reactions. So they are the ones who hold the body to make it equilibrium. While the applied forces are the forces applied to the body that tends to move the body. So the first step in the analysis of the body is equilibrium. In equilibrium is to identify all the forces that are acting to it. So that is the one important technique or one important step in solving equilibrium analysis, because you cannot solve the problem if you don't know what are the forces acting on the body. So this step can be done by creating what we call the free body diagram. So a free body diagram is basically a sketch of the body showing all the forces acting to it. So the forces may be what we call the reactive force or the applied force. So the term free means that all the supports are removed and replaced by forces, which is commonly known as reactions, and they can exert on the body. So it is important to master the concept of creating free body diagrams, since it is a fundamental skill in the engineering discipline. So the construction of FBD will turn a physical problem into a form that can be analyzed and solved mathematically. So the forces acting on a body can be divided into two categories. So this is what I said in our previous slide. So the first one is the reactive forces or the reactions. So these are forces that exerted on the body by the supports to which it is attached. So it is what the supports are the ones who holds the body in place so that it will not move and it will stay in equilibrium. Well, the applied forces are forces acting on a body that is not provided by the supports. So these are external forces that are generally not from the support. It may be the weight of the structure and other forces applied to it. So these are these two forces must be included and shown in the free body diagram. So these are the steps in creating free body diagram. So the first one is sketch the body, assuming all the supports are removed. Next, draw all the applied forces and label it on the sketch. So you can write the magnitude if it is given, and if it is not, then you can write a variable so that you can include it, and make sure to specify its point of application correctly. So example of this is the weight of the body must applied to the center of gravity of the body. So the forces must be placed in a right position so that if we will try to solve for the values of the forces and the reaction, we can get the correct answer. The third one is draw all the reactive forces, or shall we call the reactions, and label it in the sketch. If the sense direction of the reaction is unknown, basically most of the problems in equilibrium analysis, the reactions has no, shall we say, there is no final direction yet. So you must assume the right direction of the, shall we say, you must assume first the direction of the reaction. So in case you have wrong assumption in the start, what will happen is you will only get a negative value in the answer, but still you will get the same, shall we say, the same magnitude. So as a positive result means that the assumed direction is correct, while the negative result means that the correct sense or direction is opposite to the assumed direction. So basically, if you get a negative answer, you just change the direction of the reaction, because the direction is opposite to the assumed direction. So the fourth one, all of the important angles and dimension must be also indicated in the sketch. So basically, if you're taking moments, summation forces, vertical and horizontal, the angles of the forces and the distance for summing up moments must also be indicated in the free body diagram so that you will get the right answer. So let's try to discuss first the different types of support reactions. So one of the most difficult steps in creating free body diagram is the determination of the support reactions. So let's discuss different types of support reactions that are presented. So let's try first, the most basic one is the flexible cable. So a flexible cable is a cable that exerts a pull or tensile force. Basically, it is only tension. A cable cannot resist a compression force. So meaning, if this is a cable, so the forces on it must always be in tension. So we will use quantity T. We cannot apply compressive force. So if we replace this one with compressive force, say C, compressive force, so that is very wrong, because we cannot compress a cable. We can only pull or apply tensile force onto it. So with the weight on the cable neglected, so we just neglect the weight of the cable forms a straight line if its direction is known. Removal of the cable introduces one unknown, which is the magnitude of the force exerted by the cable. So commonly we use the variable T. Magnitude T stands for tension in the direction of the cable away from the body. So away from the body. So if we have here a ball or a body then attached to a cable, and this one right here, if you want to draw the free body diagram of the ball, what will happen is you will apply the tensile force away from the body. So, away. But if you want to draw the free body diagram of the wall, so what will happen is, you will put the tension away from the wall. So, it's always away from the body. Now, you cannot interchange the direction. Example, if you put it like this is the tension, so that is wrong. So, the next one is frictionless surface or single point of contact. Or you basically just single contact on the surface, which is at a certain or a single point contact between the surface and the body. So when the body is in contact with a frictionless surface at only one point, the reaction is a force that is perpendicular to the surface. So acting at one point, which is the point of contact, this reaction often refers to simply as the normal force. So we will use N. So perpendicular, meaning if this is the surface, the force must be forming 90 degrees from the surface. So that's why theta is placed there, because if we write it here, if this is theta and this is the force, normal force, so this is 90 degrees. So what will happen is, this is also theta, this one right here, because this one right here is 90 minus theta. So since all of this is 180, so 90 plus 90 minus theta plus theta is equals to 180. You will get this one as theta. So that's how you get the direction. So it is normal to the, or shall we say perpendicular to the surface. So you will interchange. So example, if this is a slope, if this is A over B, so what will happen here is the force will be changed, or the slope will be changed with B over A. So it depends on what the given. If it is a slope or a angle, it's still normal or perpendicular to the surface. So next is roller support. So actually roller support is somehow equivalent to the previous one, which is the frictionless surface. So it can only exert the same one force, so same variable, the normal force, and the magnitude of the force is thus only one unknown introduces in the free body diagram. So the same as the previous reaction. Next is if there is a friction or single point of contact. So a friction surface will introduce a frictional force, which is F. So we have the normal force from the frictionless, but since this is a surface with friction, so we will introduce another force, which is the friction force. The friction force, by the way, is parallel to the surface. So if this is the normal force, which is 90 degrees to the surface, this is the surface, what will happen is the friction force is parallel to the surface. So basically, the two forces forms a 90 degrees. So that's how you calculate or assume the direction of the forces. Next one is the pin support. So a pin support is a cylinder that is slightly smaller than the hole, which is this one. This is the pin. So it will, if you look at it in three-dimensional, it will look like this. Right one. This is the pin. So a body is attached to it with a hole. Of course, the body has a hole. Example, this is the body. So which is this one. Then the reactions there is basically there is only one force or one reaction R, but we don't know the direction. That's why it's always assumed to get the components. So basically we break down already the reaction into components, which is the vertical and horizontal. So, neglecting friction, the pin can only exert a force that is normal to the contact surface, shown as R in the figure at B, which is this one, and the angle theta that specifies the direction of R. Alpha is unknown because the point where the pin contacts the surface of the hole is not known. So, more commonly, this is the most common way in solving pin reactions. The two unknowns are chosen to be perpendicular components of R, which is the it may be X and Y, vertical and horizontal, and you may also rotate it depending on the problem. But this is the most common one. So, if you want to get alpha, so you just calculate it from the components by using the arctan. So, if this is alpha, in this problem, basically, this is Rx over Ry. But if you want the angle theta here, if theta, you interchange this one with Ry over Rx. So, to calculate the magnitude of R, that is square root of Rx squared plus Ry squared. So, that's why this is the most common way in solving pin reactions. Next one, the last one is the cantilever support. So, cantilever support or fixed support is a built-in support which is preventing all kinds of motion. It prevents translation and rotation. So, in pin reactions, there is no couple reaction because you can rotate this. We can rotate this body along the pin. So, we can rotate it anywhere because there is no translational, shall we say, rotational effect. Same goes by with the roller. There is only one support here because we can, there is no support here because we can move it along the surface. We can move it here in this direction, and we can also rotate the body. This one, we can rotate this one. So that's why there is only one reaction because it only resists movement along this direction. It resists movement in that direction. Because reactions in nature are the one that is resisting the movement of the body. So since this is resisting both rotation, you cannot rotate this. If you try to bend this one, this will not rotate in this direction. It will stay in this position. So that's why there is a couple reaction. You cannot rotate it. You cannot move it upward and downward. So there is a vertical reaction, and you cannot rotate it in this direction or translate it in this direction. So there is another reaction. So there are three unknowns for the cantilever support or the built-in or fixed support. Two forces and couple, single couple. So let's have here an example. So the homogeneous 6-meter bar AB in the given figure is supported by a vertical in the vertical plane by rollers at A and B. So we have here two rollers at both ends of the bar and a cable at C. So the mass of the bar is 50 kilograms. So we have the mass of the bar. So draw the free body diagram of the bar AB and determine the number of unknowns. So to do that, first is we calculate the weight of the bar because the only given is the mass. So the weight is simply using the formula mass times gravity. So we get 50 kilograms times 9.81 meter per second squared. So we get 491 newtons. So the location of the weight must act on the center of gravity of the bar. So we have 6-meter bar. So basically, the location is at the center of the 6-meter bar, which is at 3 meters. So at this point, so this must be 3 meters. So this is 1 meter, basically 1 meter, and this is 2 meters. So this is where the weight, so obviously weight is acting downward. So that is 491 newtons. That is what we call the applied forces. That's the applied forces. So next is the reactions. So the reactions, basically you have two roller supports and a cable. So for the cable, we will have a tensile force, one unknown, acting away from the body. So this is it. This is the tensile force. Then we also have the roller supports, which is normal to the surface. So as you can see, the surface at A is horizontal. So the normal reaction is perpendicular to that which is going upward. So that is normal at A. The surface at B is vertical. Therefore, the location or the reaction at B is horizontal, so that it is forming a 90-degree from the surface. So this is normal at B. So this will be our free body diagram. It will look like this. So as you can see, we have three unknowns. So this is solvable using the equilibrium equation. So because we have three equations, summation forces x, summation forces y, and summation moment at any point. Then we have three unknowns, which is two normal forces and tension in the cable. So this is our final answer for the free body diagram. So the next one is we have here a homogeneous 250 kilogram triangular plate in the given figure is supported by a pin at A and a roller at C. Draw the free body diagram of the plate and determine the number of unknowns. So let's first calculate the applied forces, which is the weight of the triangular plate. So the weight of the triangular plate is, shall we say, mass, which is 250 kilograms times 9.81, so that is 2453 newtons. Its location will be at the center of gravity on the plate. So the center of gravity is, if we already know the center of gravity, formula for the triangle, so if this is B, so this one right here must be 1/3 of B. So if this is H, this one right here is 1/3 H. So this is, the other side is 2/3, of course, 2/3 B, and the other one is 2/3 H. So this will be the location of the weight. This one right here. So this is 2453 newtons. Then this one is 0.2 meter, and this one right here is 0.4 meters. So this one here is 1/3 of 0.35. So I believe that is 0.116, or shall we say in fraction, 7/60 meter, and the other one is 7/30 meter. So we don't need these two distance right here, because the important one is this two, 0.2 and 0.4, because if we calculate the reactions, we will not use these two values here. We will only use 0.2 and 0.4. Then for the reactive forces, we have AY, because this is spin, so we will resolve this into vertical and horizontal force, AY and AX. Then for the C, we have perpendicular to the surface, so this is 90 degrees right here. So the angle with respect to vertical is 30 degrees. So you just change the slope because it is perpendicular, normal to the surface. So the answer will look like this. This one. This is the same to our previous answer, which is this one. We just write here normal at C. So there are three unknowns, two forces from the pin and one from the normal force or roller support at C. then the one active forces, which is the weight of the triangular plate. So let's have our last, assume this is the last problem, last example. So the beam ABC built into the wall at A carried or supported by a cable at C, then attached to the wall in this part. This is the cable. Then we have a distributed load, carries a 6 feet distributed load. Actually, this is 3 feet. 3 feet distributed load. Over part of its length as shown in the given figure, which is 1,000 pounds per foot. So the weight of the beam is 70 pounds per foot. Draw the free body diagram of the beam. So according to the problem, the weight of this beam right here is 70 pounds per foot. What does it mean is that if we take 1 foot, example this one right here, so this is 1 foot, the weight of this one is 70 pounds. If we take another foot, 1 foot here, so that is another 70 pounds. So if this is 3 feet, there will be 370 pounds because that is 70 pounds per feet of the beam. So if you want to get the weight of the beam, what will happen is 70 pounds per foot. Then the length of the beam is 8 feet. So that will be the weight of our beam, which is basically 560 pounds. So that's how you get the weight of the beam, which is this one. Because we have how many 70 pounds? 1, 2, 3, 4, 5, 6, 7, 8. So each of that is 70 pounds. Assuming every block is 1 feet. So we have 1, 2, 3, 8, 70 pounds per feet. So that's how you get the weight. So weight obviously acts on the center of the block or the rod or the beam. So this is basically 4 feet and this is another 4 feet because it is 8 feet. Then for the distributed load, what will happen is we get its resultant. Its resultant is acting on the center, which is 1.5 feet. 1.5 feet because it is 3 feet. Then the resultant is the area from our previous discussion on distributed loads. So that is 1,000 pounds per feet times 3 feet. So we will get 3,000 pounds. So what will happen is, let's try to solve the other one. So we have here the tension of the cable. So we don't know the slope here, but we have a given here 6 and 8. So that is the rise over run. So we will now use the slope 3, 4, 5 because 6 over 8 is equals to 3 over 4. So this is the slope. And the other one is the fixed support. So we have 3 unknowns here. We have AY, we have AX, and we have couple at A. So the answer will look like this. So we have here 3,000 pounds, which is 1.5 feet because the centroid is at the half of 3 feet. Then we have the weight, which is 560 pounds. So its location is 4 feet because it is in the center of the 8 feet beam. Then we have the tension T with a slope of 3 over 4 because the slope here is 6 and 8. Then we have 3 unknowns, AX, AY, and CA from the fixed support at A.